So welcome to the 29th, which I find interesting, of our Covalent Academy webinars. This is another in our Advancement in Instrumentation series. And this one is Adventures in Wavelength Dispersive X-ray Fluorescence. I could have just said WDXRF. Flexible element analysis for thin films and more. And we will basically, as you know, go through a whole bunch of housekeeping right now before we go to our next slide. So the back up one, sorry, that was my fault, Meredith. So the webinar itself is being recorded and will be available on the Covalent community. And we'll talk to you at the end of the webinar and tell you how you can sign in to see not only this webinar, but the other 28 before it. Also, the slide deck that's being presented will be posted up there. And we'll also post the questions and answers session that we do, as well as other questions and answers, all up in a form that you can get to. For questions and answers, please use the question and answer button. That's so we can keep a nice flow so Meredith can do a good job doing her webinar. And we will answer as we can, depending on what time we have. And if we don't answer them, they will be available in the up on the website later on. So let me give you a few words about Covalent. And Covalent itself, we're based in Silicon Valley, in Sunnyvale. We're an analytical lab and an expert analysis group for both advanced materials and device innovation. And I'm not going to go through all of those slides since this really isn't the main thing, but you can see a little bit about us. We have more than 50 instruments, nearly all of them advanced instruments. We'll talk a little bit about that later on. And essentially, we offer both analytical services as well as method development. We can help you with temp staffing. Covalent is put together to help you solve your problem. So the more you explain the problem to us, the better help we can do. If you want to just come in and get a measurement, we can do that. If you want to come in and talk about why you need a measurement, we can certainly help you much more. We have a very flexible business model. We have a rich network of partnerships, which makes things like this Advancements in Instrumentation series available. And the last slide is actually, the last part of this slide is actually a little bit out of date because we now have 60 people working for Covalent. Next, please. So I'll give you an idea of our technical groups and organization. We're split into a number of groups, basically looking at different parts of the market or in instrumentation. We have a failure analysis group. We have a big electron microscopy and scanning probe microscopy group, including, of course, TEM and STEM. A strong optical microscopy group, a very strong X-ray characterization group, and we're going to talk about one of the tools today. Do elemental and chemical composition, particle analysis, materials properties, surface spectroscopy, and a number of other things that aren't on this list or on the website. And so if you need it, you can always talk to us. So instrument partners are very important to us. And Ragaku, who Meredith works for, is our oldest instrument partner. This partnership was announced in the fall of 2018. And we are home to Ragaku's Silicon Valley Semiconductor Division Metrology Lab, which includes, at this point, a smart lab, a micro CT, and an AZX 400, which will be the tool we talk about today. This lab is continuing to expand, and over the next 6 months, we will be adding new tools and greater capabilities in. As you can see, we have a number of instrument partners, and they're very important to us because they allow us to basically work with cutting edge instruments and new instruments. As we were talking before we went on the chit chat, the ability, instruments that are being released now can now do things that a few years ago, even 2 or 3 years ago, couldn't be done. And so that having advanced instruments makes a big difference to what you can actually do to help your customers solve the problem. So now I get to introduce our speaker. And Meredith Beebe, she works for she's the semiconductor X-ray metrology specialist at Ragaku, has 20 years in the semiconductor industry. which sounds like a long time to you guys, but I'm slightly older than she is. She is
Sounds like a long time to me too, Chris.
She is a subject matter expert, and she is very good at helping people understand both what the tools can do for them and how they can basically work with the tools to get what needs to be done. And now I suggest you sit back and relax like I'm going to do and listen to a very good webinar. All yours, Meredith.
Thank you, Chris. I appreciate this opportunity from you and Covalent. And I want to say thank you to all the attendees. I appreciate you taking time out of your day and your interest in WDXRF. Okay, so this is my outline. Today we're going to go through the WD wavelength dispersive X-ray fluorescence. We'll go through the technique overview. I'll talk about the principles of X-ray fluorescence. We'll talk about the differences between sequential and simultaneous spectrometers. I'll review the qualitative and quantitative methods available. And then I'll also compare WDXRF to the sister technique of energy dispersive XRF. I'll review the Rigaku AZX400 spectrometer. I'll talk about some application studies, and then we will wrap things up and have our Q&A. Before I get to the technical details of WDXRF, I wanted to first review some key points of the WDXRF and the AZX400. In WDXRF, we have a non-destructive measurement that is able to detect a wide range of elements. This element range is beryllium through uranium. We are particularly suited to detect light elements of boron through aluminum, and I'll talk more about that later. We're also able to handle a wide range of samples. And so we have sample adapters that can fit on the AZX. And this allows us to be able to measure various sample shapes and sizes. We can measure wafer coupons, sputtering targets, whole wafer samples. We can almost accommodate any size sample up to a 380 millimeter diameter. The AZX400 can also do film thickness measurements from angstroms to microns. All right, first, let's get back to the basics. This is a slide showing an overview of the principles of the X-ray fluorescence technique. So first, we have a photon of sufficient energy from our X-ray tube that strikes an inner shell electron. This photon ejects the electron from the atom and creates a vacancy. This configuration is unstable, however, and the atom is at a higher energy. When an electron relaxes to fill this vacancy, an X-ray photon is emitted. The energy of this emitted photon is the difference of the binding energies of the two orbitals. So we can measure this energy of this photon, of this emitted X-ray, and identify which element it came from. Plus, we can also look at the intensity of the emitted X-rays, and that can help us identify the quantity and the amount of material present in our sample. Here's some fundamentals of the WDXRF. So this is what's happening inside the measurement chamber. First off, we have an X-ray tube here, and it's directed at an area of our sample. This gray disc is an example of a silicon wafer. These are the fluoresced X-rays that are emitted in all directions from our sample. And here is the process where the process of XRF that I spoke about on the previous slide, this is where that process is taking place. Next, these emitted X-rays move to a crystal monochromator. These crystals have different lattices to optimize and capture certain wavelengths of elements as defined by Bragg's law. So then we place a high sensitivity detector at the proper 2 theta angle for a particular element. And then that's how we're able to detect multiple elements that are present in our sample. Here's an example of a sequential WDXRF tool. This is a WDF spectrometer. We have our X-ray tube here again. We also, in sequential WDXRF, can use a primary beam filter, and this helps us to reduce or eliminate diffraction effects. So we have our X-ray tube, the primary beam, and then the X-rays are fluoresced off the surface of our sample. They move through a slit and then bounce off of a crystal. And as I said before on the previous slide, X-rays coming from the sample diffract with different wavelengths in different directions. So in a sequential WDXRF tool, we can move the crystals to select the element wavelength that we want to capture. And then we also move the detector. The detector is on a goniometer, and then it's able to move through different 2 thetas to collect intensities of different wavelengths of different elements. So this is how we get the sequential WDXRF name, that we measure one element after another with this system set up. Next, we have the simultaneous WDXRF. So again, here is our X-ray tube. The X-rays hit the sample, but here our diffraction crystals are fixed. Our diffraction crystals and our detectors are fixed. So in a simultaneous instrument, a tool can be configured with specific channels. And in these channels, we pair crystals and detector combinations that are optimized for particular elements. So with simultaneous WDXRF, we're able to measure the elements in the sample all together simultaneously. Now we'll talk about qualitative and quantitative methods. In qualitative, we can do a qualitative scan in WDXRF. So this is just moving the detectors through a broad 2-angle theta range, and then we can just detect for we can look for the presence of different elements in our sample. Before I talk about quantitative methods, I want to discuss film thickness and X-ray intensity and their relationship. This is an example of a single element film case, in this case copper, and we can look at the relationship of the film thickness to the X-ray intensity. So we have varying levels of thickness of this copper film. And here, when we have a thin film, the relationship between the film thickness and the X-ray intensity is linear. This is because all the X-rays from our film are escaping and are able to be detected. However, as our film gets thicker, not all the X-rays that are present and not all the copper X-rays present in this film are able to escape. Some of them are self-absorbed. So in a thicker film here in this region, from the X-rays, copper X-rays, fluoresced X-rays from the bottom of the film might not make it out of the stack to be detected. And when we are in this part of the response curve here, when the curve starts to flatten, the intensity is proportional to the concentration. So I'm going to talk more next about the fundamental parameter method. And this is a model that can help us to model this response area of the curve. So we have quantitative methods that are basically standardization models to address thin films and bulk samples. So I already touched on fundamental parameter. In fundamental parameter technique, we can use pure element or type standards, and it's a fully quantitative measurement. Type standards are standards that are similar in composition to the unknowns that we're going to measure, and using a type standard helps to improve the accuracy of our FP calibration. In the AZX 400, we also have library standards. So this is more of a semi-quantitative measurement where we have computer-stored calibration parameters. And this is especially helpful when calibration standards are not available for our analysis. And something to note, the density of your material is also important when we're quantifying in the linear thickness range. So we can also use empirical models. And in empirical model calibration, we rely on a suite of calibration standards. And this range of standards covers the thickness and the composition values that we expect from our unknown product. Here's an example of the FP and empirical calibrations. In fundamental parameter method, we plot for our calibration measured intensity versus the theoretical intensity. So the measured is the intensity that we obtained when we measured the standard on our instrument. And the theoretical intensity is calculated by the fundamental parameter method. So we build our stack and we tell the FP method what is present in our sample, the thicknesses, and then it can calculate, taking into account absorption effects and other modeling effects, the theoretical intensity. So we're looking at theoretical versus measured intensity. This is theoretically linear usually, and we can do thickness and composition analysis simultaneously, and we can do multiple layers. Also, because of the FP method, we can also get by with just using a few standards, and we can also use pure metal standards. We don't have to have the type standards that match the product exactly. In an empirical calibration, we plot measured intensity versus the thickness, the known thickness or composition of our standard. So we measure the intensity, we plot that versus the standard value, and this isn't typically linear. And it also can only analyze, we need one curve for each thickness or composition measurement that we need. We can't do it simultaneously like we can with FP. You also need a range of standards for each element or each thickness or composition. Anything you want to measure, you need a separate calibration curve for that in empirical. Here's a comparison of WDXRF and the sister technique, energy dispersive XRF. First, comparing the system setups, as I've already reviewed, we, in the WDXRF, we have an X-ray tube, the fluorescent X-rays go through a slit. We highly select, and this is how we're able to get great spectral resolution in WDXRF, that the fluorescent X-rays go through a slit, and then the analyzing crystal, and then they're sent to a high sensitivity detector. In EDXRF, it's a more simple setup of an X-ray tube and then an energy detector. Typically, we use the silicon drift detector. And we are dependent on our resolution in the EDXRF measurement completely on the capability, the resolution of this energy detector. In WDXRF, we can measure the element range of all the way up to the light elements of beryllium. And in EDXRF, typically the elemental range is aluminum through uranium. In WDXRF, we're able to get a little bit lighter elements of the low Z elements because the measurement's done in vacuum. And also in EDXRF, the detectors typically have a beryllium window, and elements lighter than aluminum can be absorbed in the beryllium. For the quantitative method, we have the advanced FP, as I already discussed, that enables us to measure thickness and composition simultaneously. In EDXRF, we typically use the empirical method that cannot do thickness and composition simultaneously and requires a range of standards at different thicknesses and composition. Our analyzable structure, because we have the FP method, again, we're able to take into account absorption effects of the other layers, and we can analyze complex compounds and multi-layered samples. In EDXRF, it's typically a single layer or a few layers of a simple structure. In WDXRF, we can measure at less than 1 nanometer, and EDXRF typically is reserved for films of a 10 nanometer thickness or more. Here's an example. Here we wanted to highlight the high spectral resolution of the WDXRF technique. So we overlaid data of a 1 micron aluminum film with the same film measurement on an EDXRF. As you can see in the red, the aluminum and silicon K alpha peaks that are pretty close together, they're neighboring peaks, are completely resolved in the WDXRF data. In EDXRF, this ever-present silicon peak on our silicon wafer samples tends to influence the aluminum peak, and we don't get as good resolution when we use the energy dispersive XRF. Here's another example of an overlay comparing the two data techniques. This time we have a GST film with germanium, antimony, and tellurium. And you can see we can completely separate the antimony and tellurium peaks that are difficult to fully resolve in an EDXRF measurement. Here's the sequential wavelength dispersive XRF. This is the same tool that's at Covalent. And this is the Rigaku AZX 400. We have a 4 kilowatt sealed X-ray tube. It's a sequential type goniometer. We have the primary beam filters to help eliminate or reduce diffraction. And we can measure with a range of spot sizes. So our measurement spot size can be up to 30 millimeters in diameter and go all the way down to 0.5 millimeter. We have the flexibility to measure that wide range of sample types, as I discussed, because we can apply different sample adapters to the tool. So we can load wafers or coupons and sputtering targets. We also have an auto wafer loader that can accept wafer samples, whole wafer substrates without any manual handling necessary. Again, we can analyze from beryllium to uranium. And the range for composition is from ppm to percentages, and the thickness range is from angstrom to microns. This tool is especially well suited for a process R&D that has a low volume but a high product mix. So now we'll discuss 3 different applications of WDXRF. First, I'll talk about MRAM, then sputtering target, and PZT. Magneto random access memory. MRAM is an important technology for state-of-the-art technology nodes. The fundamental memory element is a stack of thin films on the order of tens of microns. The composition and film thickness are important for the functional behavior of these devices. And this is an example layer stack. And the primary feature here is this structure called the magnetic tunnel junction, the MTJ. So here we have the MRAM stack again. And what makes this MRAM samples a good adventure for WDXRF is the MTJ structure has the light elements of magnesium and boron that we're able to detect with WDXRF. It has high elemental resolution. So we need high elemental resolution to resolve in overlapping peaks in this structure. We have that with the WDXRF. Also, it has the high precision required for thickness and composition repeatability measurements required in fabs for statistical process control. So here's an analysis example of the magnesium oxide layer. Because tantalum is also used as a cap or barrier around the MTJ structure, it can be difficult for EDXRF to resolve the tantalum from the magnesium. But as you can see in WDXRF, we're able to fully resolve the tantalum peak from the magnesium peak. Also in EDXRF, sometimes we get higher backgrounds because of a neighboring silicon K off the peak. But again, with WDXRF, we have no influence of the silicon peak on magnesium, and we're able to separate out the tantalum. And here's some more analysis results of the magnesium oxide layer. This is an example of the FP calibration for magnesium. And we have these ultra thin magnesium thicknesses that range from 4 to 16 angstroms. So this technique can see the 1 angstrom steps and ultra thin thicknesses of 5 angstroms, which can be difficult for other methods. We also have a 10 times repeat measurement of the magnesium for each of these samples, the 4, 8, 12, and 16 angstroms. As you can see, we achieved relative standard deviations of less than 1% for each of these films. And these low RSDs we get from the WDXRF demonstrate the technique's excellent precision. And this is really what makes these tools so helpful in the semi industry for process monitoring. Through process development, as these structures are built and they're dialed in during their process control, our tool has the high precision necessary for process monitoring, and it's extremely useful for full statistical process control in the fab. The second application is sputtering targets. So sputtering targets are used to create thin films and sputter deposition tools. The composition of the starting material of the target is going to determine what you're going to deposit onto your wafer. So we care about the composition of the targets, and also we can detect trace elements that might be present in the target besides the intended sputtering target composition. This is a good adventure for WDXRF because it's non-destructive and no sample prep is needed for analysis. Again, we have that wide elemental range of beryllium through uranium, so we're able to handle various sputtering target materials. And also we can use library standards, again, for a semi-quantitative analysis if we can't locate type standards available for the sputtering targets. The ACX can also accommodate the large sputter target samples. So here's a picture here where we have a sputtering target in one of our sample adapters, and this is loaded on the ACX. So we can actually measure directly these sputter targets, or we can measure the wafer samples that come from the sputter target deposition. So we can measure both the actual target and the wafers that have been depped. Here's an example of the target qualitative scan that is from a sputtering target mainly composed of lead, zirconium, and titanium. We use primary filters here on the ACX for this measurement because we wanted to suppress the background from the high intensity X-rays that we saw from these elements and avoid any counting loss errors for lead and zirconium. So we see these dominant peaks of zirconium, lead, and titanium that we expected from the composition of the target. But in this qualitative scan, we were also able to detect trace amounts of silicon and aluminum. Here's an example of the same target. We did a 10 times repeat measurement at the center of the target. And for the lead, zirconium, and Ti oxides, we achieved an RSD relative standard deviations of 0.2% or less for the dominant elements. For the trace elements of silicon and aluminum that we saw a RSD of less than 3%. We also took this target and did a 25-point map across the surface to demonstrate the distribution of the elements across the target. For the lead, the zirconium, and the Ti, we saw less than 0.4 or at 0.4 RSDs across the surface of the target. And for the trace elements, this data was particularly interesting because we're able to provide maps of the distribution of these trace elements, these unintended elements present in the sputtering target. So we can not only measure these and quantify them, but then also show the distribution of them across the target. Last application is PZT. Like MRAM, PZT is also an application of thin film stacks where composition and thickness affect the functional performance and reliability of the device. The piezoelectric material is used in various sensors and MEM devices, and this is an example of the film stack. We have our silicon substrate, a silicon dioxide, and then a titanium oxide, then a platinum layer, and then on top of that is our PZT. This is another good adventure for WDXRF because we have the high spectral resolution needed to separate the lead, platinum, and titanium overlapping peaks. Also, with the fundamental parameter analysis, we can analyze complicated multi-layer stacks for film thickness and composition. And again, the ACX can accommodate PZT wafer samples or coupons. And we can also load pure metal disk standards for our calibration. Here's an example of the PZT analysis that we built in the fundamental parameter method. So this is our same stack. We have the silicon substrate, but in this case, in the fundamental parameter, we fixed the value of the silicon dioxide and also the titanium oxide. And this enables the Ti to be measured and accounted for that only comes from the PZT layer. We also used pure metal standards for lead, zirconium, and titanium. Here's a qualitative scan of the PCT sample. This was a 1 micron PCT thickness and 100 nanometer platinum film underneath. And so as you can see with the WDXRF, we have this amazing high spectral resolution, and we can completely resolve the lead, platinum, and zirconium lines that would overlap each other in EDX. Here is a 10-time repeat measurement of the PCT platinum multi-layer stack. So first we have the thickness, a 10 times repeat of the PCA thickness. And we achieved RSDs of 0.14% for the PCT and 0.15% for the platinum underlying platinum layer. We also looked at the composition of the PCT layer for the lead, zirconium, and titanium oxides. And we achieved a 0.2 RSD or less for the mole percentage measurements, repeat measurements of that layer. We also can take the composition ratios that we determine from these mole percentages, and we can compare the lead with zirconium titanium ratio to the zirconium with zirconium and titanium ratios. Just to touch on again, the ACX 400 measurement flexibility. Again, we have the different sample adapters to accommodate a wide range of samples. We have the vacuum option so that we can obtain lighter elements that pass lighter than aluminum. We have the library standards. If you don't have standards available, we can do a semi-quantitative analysis. We have the FP method and high peak resolution, which enables us to resolve complicated spectra and overlapping peaks. We also use primary beam filters to eliminate or reduce diffraction. Here's an example of just the wide range of thin film applications that we have successfully measured on the WDXRF. It's quite expansive. Okay, and so in conclusion, the key features of WDXRF is it's a non-destructive measurement, and we can detect a wide range of elements. We can do ultra-thin film thickness measurements from 0.1 nanometer. We have high peak resolution, and we have the fundamental parameter method to analyze multi-layer stacks and complicated compounds. We have the sample adapters that allow us to measure various shapes and sizes of samples. We have the library standards for semi-quantitative measurements. And we can also do the qualitative scans. If you just want to see what's present in your sample, we can scan across the entire range, or we can also focus in on smaller element groups. Thank you, Chris.
And thank you, Meredith. You're a little quicker than I expected, but that's okay. We have a whole bunch of questions, some of which we can get to, some of which we're probably not going to get to. But before we get to that, let me talk about our next webinar, which will be laser ablation in ICP-MS. And the title is Not Just Rocks. I think many of you would know that LA-ICP-MS is heavily used in the geology industry. And for mining, most mining operations use some variation of the tool. But as this tool has matured, there's been a whole bunch of applications that have to do with everything from fine heavy metals in tissues through to semiconductor applications and other types. So it should be a very interesting seminar, and it's not that far away. It's in fact on February 10th. I think I'm hosting that one as well. Next slide, please, Meredith. So if you want to learn more about Covalent's WDXRF and spectroscopy services, and you want to talk with people, then essentially you can schedule an appointment. And I think Shannon just put up in the chat how you can actually schedule an appointment to talk to us directly. Now, as part of the my housekeeping, I should mention that we actually have 2 polls that we're going to ask you very quick. And by the way, if you're a panelist, you can't answer the polls. You may as well just click them because they won't come. So they will put the polls up shortly. Please answer them for us. If you go to the next slide, please. There's the first poll, which I have to get rid of. Okay, next slide, Meredith, please. There we are. Okay. You know, I told you something would go wrong. See, it went wrong through my part, not your part. So
Not
if you,
so bad.
yeah, if you want to know how to get to the community and where all of these webinars are recorded and the slides will be put up and also the question and answer sessions will be put up, then this is one of the ways you go about it. You're looking at our website, www.covalentmetrology.com. And you'll notice up there a highlighted login button. Of course, it won't be highlighted when you go there. There will be no big circle. I had somebody actually ask me this later. It'll just be the standard login. And I promised a couple people that I would actually put a plug in also for the button beside it, which is the About Covalent button, because there you can find our careers page. And in fact, in our careers page, we have a number of job openings. As I said, we're now at 60 people and we're growing quite rapidly. So if you're looking for a career, by all means, talk to us. Next slide, please. If you press that login button, you will see these two screens. One of them is for our normal customers who are already registered with us and we do have already done jobs and work and data. And for them, their easiest way to access is to go to their normal login. And then down the bottom left, they'll find actually a link to the community. On the right, you can see community access for all others. That's a pretty simple log in, register, and and do a password. There's no multi-factor authentication like there is for our normal customer base. And you can get to all sorts of things. So like I said, there will be 29 webinars up there by the middle of next week. There's a lot of information and a lot of very good educational information. And by the way, if you have ideas about what else you'd like to see, Shannon was always happy to respond to people to see, as we get ideas about it. Typically right now, our webinars are booked through actually the summer, I think. Next slide. So now we're into question and answer, and this is where Meredith gets all worried that I'll throw her gotcha questions, which I never do, and she should know better. So
not worried.
Yeah.
Not worried.
Yeah. So let's start with a basic one, which is you talk about the light element, the ability of something like the AZX to be able to go to beryllium, the very light elements, which is a little unusual, right? And I assume it's because basically the sample's running in a vacuum. Is that the main reason that you can go to those light elements?
Yep, definitely. We have the vacuum and we also have that high sensitivity detector. It's a low resolution, but very high sensitivity. And it does not have a beryllium window like EDXRF. So we don't have any absorption of any of the lighter elements in our detector.
Okay, and I understand that because you're diffracting off a crystal, that's why the background is as low as it is and why you can get to very low ppm type counts in these types of measurements, correct?
Yep, exactly that. And that's also how we're getting that high spectral resolution. So we're able to optimize for these particular wavelengths.
Yeah. So we all know there's a price to pay for that, in that typically WDXRF systems are slower than EDXRF systems by quite a bit. And I understand that the simultaneous detection of elements makes it faster, but then you have to select which elements, right? There's no holy grail of system that will do the whole spectra really quickly in a WD formation that I know of. And I don't think it exists, right? So it's always trade-offs when you're looking at these things. So the WD, when you look at it, is really, I think, made to look at larger areas than most ED tools. I think that's true. And also, but made to look for very high sensitivity. So I can look for trace elements in materials, correct?
Definitely.
Yeah. So I have a question that doesn't have a good answer. So I'll ask the question and then we can, and which is basically, what's the interaction volume versus an EDX tool? And you're the interaction volume, where you're collecting the X-rays from. And I assume you're going to tell me it depends on the structure and the material and the various things that have to come into it. But fair to say that typically it's much bigger in WD because the spot size is normally much bigger.
Right. We can change our spot size we have a range of spot sizes we can select, but yes, you mean like the depth of analysis of the X-rays?
Yeah.
Yes, we can. It all depends on also, we have that 4 kilowatt tube that we're using. And so that is a specialized voltage to be able to excite a lot of elements at even low Z up to high Z. And so we can get good sensitivity and also get that depth, that penetration depth that we need to go up to nanometers for our analysis.
So basically, roughly, Meredith, how deep are you typically collecting information from in a sample? Say I gave you an aluminum alloy sample. Mm-hmm. How deep would you be collecting information in it?
I mean, on the order of nanometers.
Okay, so it's
yeah,
good. It can be. So I mean, you talked about sputter targets, and that raised to mind, and because Covalent's actually done it, you could use the same system to measure alloys, right? Is this this type of alloy or that type of alloy? Is that relatively common measurement using this tool?
Possibly outside the semiconductor industry, but for the sputtering targets, typically that we put the target on, or we also measure the wafers that have been depth by the target.
Yeah. Now I know that for the AZX, and now I'll raise one of the issues. It is a tool that measures with the sample basically upside down, if I think about it that way.
Yep.
Correct?
Yep.
So, and as far as I know, you don't do much powder measurements that way. Is that correct? Or is there a way to measure powders in an AZX?
There is, but that is not typically what we measure for in the AZX tool specifically.
Okay. So you picked a number of semiconductor samples, and I understand why. But what about measuring glasses or insulating materials or that type of thing? Any issues there?
Yeah, no, we had that wide. I showed that one slide with the wide range of materials, and we can handle quartz and the sputtering targets and other things outside of the thin film wafer substrates.
Yeah, so now I have a question that is entirely different. We'll see how your answer goes to this one. So if I'm using a WDXRF, say for process control, would I not need to have that tool in-house?
Yes, you could have the tool in-house and use it to monitor for your SPC. Yes, that would be ideal, I guess, depending on how often your SPC measurements are done.
Yeah, as an instrument manufacturer, I think that would be my answer. From Covalent's point of view, it depends very much on whether you're measuring every sample, every 100th sample, how much of your tool is tied up in a day doing SPC.
Yes, exactly. I think it would be especially helpful, especially as you're in your process development and you're dialing in your structures, that you could continually monitor. And then once where you get them where you want them, comparing them to the reliability or functional performance, then you can put them on the SPC and control the process and watch it in the fab.
Yeah. So accuracy has come up in a couple of the questions. Always a tricky issue, depending on whether you're running calibration samples or whether you're running FP or various types of things. You have any feel for, what the actual accuracy is when you're running FP in the libraries versus, say, if you could actually build a set of calibration samples? And again, I know it'll depend on sample and structure and everything else, right?
Yeah, we consider the library standards semi-quantitative, and when we look at the full FP quantitative method, I would say using the library standards, maybe a 20–30% difference you might see in your accuracy.
But your precision will still be every bit as good, correct?
Right, right. I hesitate to say this to customers, but at the end of the day, maybe the number doesn't matter as much. We're in a precision game here. So if you have your structure or you have your process where you want it, we can monitor that within a very tight precision.
Yeah. The sensitivity of the elements, if I remember in tools of this type, you have different crystals and different detectors, right? Depending on which elements you're looking for.
Yes.
Does that mean that sensitivity changes depending on what elements? So we're less sensitive to light elements than heavy elements or anything? Is there any general rule?
Yeah, definitely compared to EDXRF and WDXRF, we're more sensitive to the light elements. And then the heavy elements is probably fairly comparable.
Okay. So I'm reading questions as we're talking in case you, if you wonder why I'm, so here's actually a good one we didn't cover. They're all good, by the way. The incident, what is the incident energy of the X-ray source, or are there different sources available in tools of this type?
Oh, it's a rhodium source and it's a 4 kilowatt source. Is that?
Yeah. Do you remember what the wavelength for that source is? I don't, so.
Oh, it's not monochromated. So it's all the spectrum that it brims along to. Yeah. Yeah.
So that's why you do the rejection on the detector side with the crystal then.
Yep, exactly.
Yep. Okay.
And then we have the primary beam filters to eliminate any diffraction effects.
Yeah. Are there different sources available? I mean, or is rhodium the only one that you know of that's typically
I believe
used?
rhodium is the only one, but I could double check that for you.
Yeah, we'll get an answer. We'll make sure in the question and answer that we post that we do that. Now, I have a question that I'm actually going to answer, which is the interest would be if you have a layer under other layers, can you use WDXRF? And the answer to this is always the same. It depends on the structure. You have to be able to get the X-rays out in order to be able to measure them. So if it's covered in something that basically eats the X-rays from the layer of interest, then the answer is no, you can't do much with it. But most structures, in fact, a number of structures can actually work out quite well. And we do a lot of buried layer problems that I think nearly all of the ones you showed, Meredith, were buried layer problems, in fact.
Yep.
Yeah. So
yeah, we have also the FP method, which takes into effect the absorption effects, and we have that high spectral resolution. So typically we can look at the multi-layer stacks.
Okay. And then I have a question that says, could we compare WDXRF accuracy to RBS? And the answer is yes, RBS is much better, but RBS always is much better for almost any accuracy, depending on the nature of the type of thing you're looking at. You get into complex structures, you have a lot more problems when you're dealing with RBS. So
yeah, and again, this is a precision game we're playing here with WDXRF. We have our process dialed in, and we have this excellent precision.
Or you basically have quantitative calibration samples that you can use, and then build it up that way. So I noticed that when you covered the beam size, it went from something like 50 millimeters down to 500 microns, I think, is the way, which really means that you can use the tool if you're looking at big things. You can use it to basically get you a much larger spatial average, or you can dial it down to very small areas. Does the tool map? I mean, if I got well, you showed me a map.
Yeah, yes.
Yeah. So
it definitely maps, and we can also take advantage of those multiple sample sizes to also, again, the sputtering target example, when we saw those trace amounts of silicon and aluminum, we can use a larger spot size for those measurements to generate more intensity for our detection of those elements that are present only in trace amounts.
So we talked about alloys, we've talked about glasses, we've talked about semiconductor samples. Anything else that comes to mind, Meredith, that you would say people use it quite a bit for. We should say, by the way, and you mentioned it, but from Covalent's experience, that we do a lot of very odd shaped samples. We can do wafers, and we love when wafers come in, but we get little pieces of material that have to be held to do various things too. And also, I remember that the tool can handle very heavy samples, right? What's the upper weight limit? Do you remember?
Oh, what is the upper weight limit? I have to double check that for you. Maybe on the order of tens of pounds.
Yeah, that's what I remember. Something like 30 or 40 pounds. In fact. Yeah. So you can take very big parts. In fact, we've done machine parts for people that want to see what they actually produced over time. Okay. Anything else you want to talk about?
No.
See, somebody just typed me 30 kilograms, 66 pounds.
66 pounds. Yep.
Thank you, Joe.
Thanks, Joe.
I knew somebody would be able to answer it. Anything we've missed, Meredith, that you can think of?
I don't think so.
Okay. In that case, we're actually going to say thank you very much to our audience and the ones that stayed with us through all of this, which was a good thing. I have run out of questions, in fact. So here's a question. It's actually a good question. So carbon and lead peaks overlap, I'm told, in a WDXRF. But the characteristic energies are different in those two. Is that because of the detector crystal choices, or how does that work?
Sometimes we do have overlapping peaks. It's the same wavelength, but different amplitudes. And then we also have, that's why we have the pulse height analyzer to help us further filter out into the detector to just select, to filter out some overlap that can be there with the wavelengths.
And we just had 3 more questions pop up. See there? Somebody wants to do thin films of niobium in the hundreds of nanometers. That doable? To measure layer thickness? Yeah, I thought so, but I'd ask you.
Yeah.
How long does the measurement take? So I load the sample, close the chamber. It depends a little bit on what sensitivity I want, which is counting time, but typically the load to measure time?
Yeah, the load to measure time. The measurement can go from maybe 30 seconds into minutes. And the sample loading is not that time consuming. So depending on how many points you want to measure, if you just want to do a center point measurement, repeatability to demonstrate the precision, or if you want to do a map across the surface, how big your sample is. If we have a wafer coupon, it can be a relatively quick measurement because yeah, we can just do one measurement.
Okay. We have a question that says, can coupons be auto-loaded? I know they can't on ours, but you can load many coupons at once, but there's no sort of handler to load coupons.
Right.
Correct?
If the coupon's too small for any of our adapters, we can also piggyback it onto a silicon wafer and load it that way.
Yeah. Yeah. We have loaded a number of coupons all at once and then used the function to go from coupon to do the measurements as a batch, which actually works out pretty well.
Yeah, and that would really help your throughput too, that you don't have to keep loading and unloading samples.
Yeah. So there was, in the last question, which we're going to answer, and then the rest, like I said, we will post all the answers and put everything up. Diffraction effects, which are always an interesting problem. So that if my sample diffracts, how do I handle that problem?
That we would use in a sequential instrument, like I discussed. We'll use the primary beam filters. If we are experiencing diffraction effects, we can select a filter to move in to help us with the primary beam and eliminate those.
Okay. What about sample spinning?
We do have sample spinning available for the center point measurement in the AZX.
Yeah, which is the other way I've seen people handle a diffraction problem, right?
Yeah,
You just
yes.
spin it and count. Okay. At this point, let me say thank you, everyone. Great sets of questions, which I enjoyed very much. And I have now basically come to the end. Like I said, we'll answer them. All of this will be up on the community. Thank you again, Meredith, for a really good webinar. And I hope the people that basically tuned in learned a lot, because I certainly did.
Thanks, Chris. I hope everyone learned something too.
Yep. Thank you, Shannon.